Here we're going to create a training and a test set, so we make sure we are not classifying data points that are contained in the training set. So let's say that we're going to use a percentage of testing cases, for example 0.25, and we are going to select a random sample from the training set. Here I'm going to pick the indexes. So from the index, the percentage of the amount of rows, right? We need to cast this as integer, right? So our test set is going to be the data indexed in these indexes, and our training set is going to be exactly the opposite indexes. We can do something like this. So here we are selecting all the cases that are not in the indexes. It's important to add that we do not want to replace, because we don't want to repeated cases, right? So we must say replace equal to false. Okay, so let's take a look to the test set. Okay, actually the shape, sorry. Okay, here we go. Let's create now that what we call a confusion matrix. We're going to address that topic of classification assessment in another video in the future, but we want to register all the cases in where our classifier makes mistakes and in where the classifier is doing correct classifications. So we're going to create a confusion matrix that will be of size 2 by 2 because we have two possible classes. You're going to understand this as soon as we print it. So we will use a data frame such that we can index from the rows and also through the columns. Okay, so our data is going to be initialized in zeros because we're going to count the cases. So it'll start in zeros, 2 by 2, and the columns are going to be the class values. Same for the index. The index is also going to be class values. The class values are all the values that our class can take. So this is our confusion matrix. As you can see, we are going to count here all the cases in where the classifier said that this is a recurrence event and the real class was actually a recurrent event. And also these cases are the one that our classifier predicted recurrence events, but the ground truth class was no recurrence events, right? Same thing here, like it's so at the end the mistakes are out of the diagonal of the matrix and the correct cases are in the diagonal. So here we can have an understanding on what are the main mistakes that our classifier is doing. Okay, so let's go and classify all our cases in the test set. Here we are going over all the testing cases. So our classification is going to be our naive Bayes classifier. And the ground truth is going to be the actual class. Recall that we haven't deleted this class for assessment Now we are going to increment the correct position in the matrix. So recall that in the row of the matrix is the classification, and in the columns is the ground truth. So we are going to increase by 1. This mistake, and this is something good because we forgot to add what we mentioned in one of our slides about the black swan paradox, which is when you find 0 counts for a specific value in some of the columns. So this is why the logarithm gets undefined, which is something here, right? So let's say that when we count the cases in where x, our data point variable, needs to match that variable value, but also the class, sometimes we may have 0 counts. So this is why we need to add imaginary counts and divide by the number of values that this variable can take. Remember, we saw that in the slides. So in this case, we need to calculate the number of values that this variable can take. So it's going to be this dot unique. And it's the length of this. And so we're going to create one imaginary count inside the logarithm, and we must divide by the count class, but here we need to add the number of values, right? Recall that this is to avoid any bias by adding counts to one specific variable that had, for example, 0 counts. If we are doing one imaginary count here, we need to normalize by assuming that we are adding the same imaginary count to the other variables. Okay, so let's run this again, and here we go. So now we can print our confusion matrix, and we got these counts. Okay, so we can see that in general most of the mistakes are done when our classifier predicts a recurrence event, but it's actually not a recurrent event. This is a false positive, right? The amount of false positives. And these are the amount of false negative, in where our model predicts no recurrence events, but turns out that the ground truth was recurrence events. Okay, that's it for implementation of the naive-Bayes classifier. Recall that this is in particular for categorical variables.